Start recording. Okay, there we go. We're recording. Okay, so we're on the first page of 6.1. And hang on a second. I'm just going to pause for just a second here. There we go. We're rolling. Okay, so all I've done so far is just mention that there's a difference between an equation and an identity. Sine theta equals 1/2 is an equation because it's only true for a very narrow range of values. In traditional algebra, like solving for 2x minus 3 equals 5, there is in fact only one solution because it's an equation. But an identity, like for example, 2x minus 3 is equal to 2x minus 3, that for sure equals itself. So x could be any number you like and it satisfies it. An identity is always true for, in this case, it's true for any angle you want. Right? You could pick, just a second ago in our calculator, we picked 17 degrees. And we found that the tangent of 17 gave us 0.3057. And then we did sine of 17 degrees divided by cosine of 17 degrees, and we got 0.3057. Any angle you want will make the left and right sides be true. It says nearly all the time. There is, of course, exceptions. The exceptions here, in this case, would be, well, what if I talk about 90 degrees? Because the tangent of 90 degrees doesn't even exist. Right? So we got to make sure that it's things that exist. You can't divide by 0 even in an identity. So we have to start thinking about values that don't exist, and what we called in grade 11 are non-permissible values. Remember that a non-permissible value is any value that results in a denominator equaling to 0. So for example, determine non-permissible values for this identity. This is an identity, right? Cotangent is 1 over tangent. This should work. This left side and this right side of this equation should be true no matter what angle I put in. But, of course, tangent of x equals 0. If you put 1 divided by 0, that wouldn't exist. So when is tangent 0? At 0 and 2 pi. Or if I wanted to say across all reals, 2 pi times k, where k is an element of all integers. What are the non-permissible values on B? Well, okay. Remember that anything times 0 is still 0? So this denominator would be 0 if the tangent of x minus 1 was 0, or if the sine of x was 0. So obviously the tangent of x equals 1 would be non-permissible. And when is tangent equal to 1? When x is pi by 4 or any multiple of pi by 4. So I would say pi by 4 times k, where k is an element of integers, right? Because remember, pi by 4, that's 45 degrees. Sine of 45 is 1. So you can't use pi by 4 for x, or any multiple of pi by 4, like, 5 pi by 4 or whatever. How about sine of x equals 0? Well, when is sine of x equal to 0? Sine of x equals 0 when x equals 0 or pi or 2 pi. So I would say when x is equal to, how about pi times k, where again k is an element of all integers. So this would have non-permissible values for these values here. This would have non-permissible values for this value here. Okay, so that's non-permissible values. All right. Verify that this equation is true for the following values. X is equal to 60 degrees. All right, let's give this a try. What's secant again? Well, secant is 1 over cosine. And tangent is, well, tangent's just tangent, right? And cotangent is 1 over tangent. All right, what is the cosine of 60 degrees? So let me put in the number first. That's 1 over the cosine of 60 degrees equals the tangent of 60 degrees plus 1 over the tangent of 60 degrees. And we have to prove that this is equal to the sine of 60 degrees. So usually what we want to do here is we want to prove that the left and right sides equal each other. So let's see. 1 over the cosine of 60. Well, what is the cosine of 60? I might need my unit circle on that. The cosine of 60 is a half, isn't it? Sine of 30 is a half, so cosine of 60 is a half. So this is 1/2 divided by, okay, the tangent of 60 now, I think is √3, isn't it? Am I right about that? Is the tangent of 60 √3? Because sine is √3 over 2 and sine over cos. So yeah, I think it's √3. And then this would be 1 over √3. Meanwhile, over here, the sine of 60 is √3 over 2. So, you know what? I kind of don't want these to be equal signs. I'm just going to put them as arrows. So I have to, my job here is to prove that the left-hand side is equal to the right-hand side. So let's simplify the left-hand side. I have 1/2 on top. Oh, sorry, hang on. I just realized I goofed this up. It's 1 over cos 60. It's 1 over 1/2. My bad. Can you fix that? All right, let's simplify this. What happens when you divide by a fraction? Yeah, you times by the reciprocal. So instead of 1 divided by a half, why don't I think of that as 1 times 2? So that numerator is really just a 2. Meanwhile, down here at the denominator, I need to kind of add that together. So why don't I get a common denominator here? I'll take √3 and I'll times it by √3 over √3. Just so I have a common denominator. And that's going to equal, let's see, moving along. They don't give me a whole lot of room to do this. That's going to equal 2 over, and that'll be 3 plus 1 over √3. So that's going to equal 2 over 4 over √3. And again, how do you divide when you're in fractions? You multiply by the reciprocal, and 2 goes into 4 twice, and look at that. That's the right-hand side that I was looking for. So that's a proof. It turns out that it is an identity. Therefore, it is an identity that, and what was the original statement again? Secant x over tan x plus cotangent x is equal to the sine of x. It worked for 60 degrees. I could have tried 30 degrees. I could have tried 45 degrees. I could have tried anything that, as long as I didn't end up dividing by 0. Right? Anything that, so obviously I could not have tried 90 degrees, because tangent doesn't exist at 90 degrees. Right? All right. B. Try it again, but this time try it for 3 pi by 4. Okay, so I'm going to go back to kind of what I had before here, and again, I'm going to try to. So that's going to be secant of 3 pi by 4 over tangent of 3 pi by 4 plus cotangent of 3 pi by 4. So that's the left-hand side. The right-hand side is the sine of 3 pi by 4. Okay, so my right-hand side is pretty easy. What's the sine of 3 pi by 4? That's still positive, and I think it's √2 over 2, right? So now let's see if we can get the left-hand side to equal that. So the secant of 3 pi by 4 is 1 over root 2 over 2, the cosine value. Oh, wait a minute. Sorry. It's a negative. Cosine of 3 pi by 4 is negative, because cosine is negative in quadrant 2. All over. Tangent of 3 pi by 4 is negative 1. Cotangent of 3 pi by 4 is just the reciprocal of tangent. But luckily for me, the reciprocal of negative 1 is still negative 1. And how do you divide when you're in fractions? You multiply by the reciprocal. And how do you divide when you're in fractions? You multiply by the reciprocal. The negatives cancel, and the 2's cancel, and I get 1 over root 2, which happens to also equal root 2 over 2, which is the right-hand side. And again, same conclusion. This is an identity. It worked for 2 different examples now. But what are the non-permissible values? Well, let's see. Again, you can't have tangent values that don't exist. So tangent of x has equals something undefined, would not exist. So for example, x is 90 and 270, tangent doesn't exist. So from 0 to 2 pi, oh, I'm counting in pi's though. So pi by 2 and 3 pi by 2. But wait a minute, cotangent of x is undefined when x is 0, pi, and 2 pi, right? Because remember, any place tangent is 0 means cotangent would be 1 over 0. It wouldn't exist there. Oh, and I guess I'll also have to think about this thing here wouldn't exist if cosine was 0, right? So it wouldn't exist if cosine of x was equal to 0, right? There's nowhere you're allowed in math to divide by 0. So when is cosine of x equal to 0? Between 0 and 2 pi. Let's see, when's cosine 0? Cosine's the x value, so that happens. Oh, actually, that's the same answer as this, isn't it? At x equals pi by 2 and 3 pi by 2. So therefore, the non-permissible values of this identity are, from 0 to 2 pi anyway, are 0, pi by 2, pi, 3 pi by 2, and 2 pi. For every other angle, I know I only tried 2, but for every other angle, that equation was true. That's what makes it an identity. You literally have infinite answers that make it true. From 0 to 2 pi, you just happen to have 5 that make it not work, because it doesn't exist there. And like I was saying earlier, the Pythagorean theorem is sometimes called the Pythagorean identity. We know that sine theta is y and cos theta is x. We also know that on the unit circle, you have x squared plus y squared equals 1, which is basically just Pythagoras. Therefore, if you substitute in that x is cosine and y is sine, you can say that sine squared theta plus cos squared theta equals 1. That is our first that we are going to use identity. And we can rewrite it in a couple other ways. We can say that cos squared theta is 1 minus sine squared theta, just basically rearranging that equation. Or we could say that sine squared theta is 1 minus cos squared theta. And just as a quick reminder, remember that when I write it like that, sine squared, you don't have to write this down if you remember this. That's like saying sine of theta all squared. Okay? Now, suppose I take this equation, I'll call it equation 1, and I divide all 3 terms in the equation by cos squared theta. Remember, you can do that in equation solving. You can divide an entire equation by anything you want, as long as it's not 0. Look what you get. If you get sine squared over cos squared, well, that's tan squared. Cos squared over itself is just 1, and you get our second identity. What if instead of dividing this entire equation by sine, or cosine, I should say, what if I divided it by sine? Well, sine over itself is 1, cos over sine is cotangent, and 1 over sine squared is cosecant. These three things have to be true any place that you don't have non-permissible values, so we can use them as our first three trigonometric identities. And we can manipulate these equations to create other equations as well, again, just by rearranging them. And notice that these identities are only true when the trigonometric functions are squared. Right? Notice it's sine squared plus cos squared equals 1. Because again, it came from Pythagoras. Right? There's no Pythagoras' theorem that just says non-squared sides added up equal another side. So notice this is not a true statement. Sine squared plus cos squared does not equal 1. Those are our first three trigonometric identities. And they're going to come in really handy. You'll notice they're on your formula sheet. You don't have to memorize them. Here's what we use them for. Simplify the following expression. Okay, so let's see. What do we know? We know that tangent is sine over cos. So I'm going to use the identity that tangent is sine over cos, and I'm going to replace tan theta with sine over cos. So basically, I have replaced this, oops, oh, hang on, didn't mean to make that big, this with this. Then down here, secant is 1 over cosine. That you do have to memorize, we don't give you that. So I just replaced, come on, thing, come on. I just replaced this thing with this. And of course, cotangent, let's use a different color, let's use pink. Cotangent is, well, it's 1 over tangent, which means that it's cosine theta over sine theta. See what I can do now that I've replaced those with those identities? I can say that when you have sine divided by cosine times cosine, those cosines cancel. So the numerator is just sine theta. And the denominator is, well, the cosines cancel, so it's 1 over sine theta. And once again, how do you divide when you're in fraction land? You multiply by the reciprocal. There we go. This thing here simplifies to that. All right, you try one. Replace these three things, cotangent, cosecant, and well, two of them. Replace the cotangent and the cosecant with sines and cosines. And then see if you can simplify this down to something else. Go for it. I'll give you a sec. Okay, let me try to catch up to you now. Cotangent is cosine. Oops, it's an x, not a theta this time. And cosecant is 1 over sine. And cosine is still just cosine. So I have the cosine of x on top, and I have 1 times anything is itself, cosine of x over sine of x. Oh, wait a minute. Sorry, I just scooped this up. Let me try that again. Cotangent is cosine of x over sine of x. That's better. that up. I forgot my sine of x. And look where that's going. Did you get that this equals 1? Because it's anything divided by itself. If you still don't see where the 1's coming from, I can remind you again that when you divide a fraction, so instead of dividing by this thing, you times by its reciprocal. And sine over sine and cos over cos make 1. All right, let's try the next one. Secant squared is 1 over cos squared. And cosecant is 1 over sine. So what does this simplify to? Well, this cosine cancels that squared and gives me 1 over cosine divided by 1 over sine. And again, in fractions, instead of dividing, you can multiply by the reciprocal, which is sine over cos, which simplifies to, what's sine over cos again? Tangent. Now, obviously, I should probably have gone for all three of these examples and talked about what the non-permissible values are. In other words, this expression here that I've made all multicolored and funky is the same as just taking theta and taking the sine of it and squaring it for every angle in the universe except any angle that would make this undefined. Like, for example, cosine could not be 0 because then I'd have tangent sine over cos, right? Tangent of 0 doesn't exist. Or tangent of 90 doesn't exist. So theta couldn't be 90. Cosine could not be 0 because secant's 1 over cosine. You get the idea. But for the most part, we'd say that these are what we call identities. All right, now we jump to chapter 6.3, and we're going to do something called proving identities. To prove an identity means to manipulate both sides of an equation independently until you've proven that they're identical. Helpful hints. Very often, start by rewriting all functions in terms of sine and cosine. Ah, yes, everyone's favorite, factoring. I had this discussion with my honors students this morning, my intro calc students this morning, that if you've made it this far, and you didn't believe your grade 10 and 11 teachers who told you factoring was important, the train's probably over for you. The ride is done. If you can't factor, you're going to hit some things in math that you just can't do. This is one of those things too. If you can't factor, you're going to be sunk. One of the more important tricks in doing identity proving is to multiply by 1. In other words, how do you find common denominators? I think we've had this conversation before, right? If you're doing something like, say, 2/3 plus 1/2. Oh, my common denominator is 6, right? So you turn this into 4/6 and this into 3/6. And I always like asking students, how did you turn this number into this? And they always say the same thing. They say, oh, I multiplied it by 2. Really? You think that 2/3 times 2 is 4/6? No, it isn't. 2/3 times 2 is 4/3. And then they'll go, oh, well, okay, I multiplied it by 2 over 2. There, you happy now? Okay, so think about it logically. What did you really multiply by? 1. Isn't that what that is 1? How did you turn 1/2 into 3/6? You multiplied it by 3 over 3, which is also 1. Whether you realize it or not, multiplying numbers by 1 is a trick you've been doing since grade 7. It doesn't change the value of the number because timesing a number by 1 doesn't change it, right? And that is an important idea when you're doing proofs. We will very often rely on the trick of, we need to make something look different than it looks right now, but we don't really want to change what it is. Well, let's try multiplying it by a 1, but it'll be a fancy 1, right? Like sine of x or sine of theta over sine of theta. That's my block letter 1. I think I'll erase that because it looks kind of ugly. But you get the idea. Simplifying using your basic algebra skills. Expanding, like for example, you have something in a bracket squared. And another thing that you learned how to do back in grade 11 is multiplying by the conjugate. You used to do that to, for example, simplify radicals. Some things to remember. Identities are not equations. Keep the sides separate. You know what you're allowed to do when you're solving equations? Well, for example, when you're solving this equation, the first thing you want to do is, I want to move this minus 3 to this side by adding 3 to both sides. You can't do that in identities. Identities, you are only allowed to work with one side at a time. Things are not allowed to cross from the left to the right. So keep the sides separate. Don't forget to use the correct variable. We've already had examples that had theta and examples that had x. They make me take off a half a mark if you suddenly, in the middle of a proof, decide to switch the variable to something new because you forgot that you weren't using theta or you weren't using x. Left-hand side has to equal the right-hand side. I'll just abbreviate that from now on. You've already seen me do that in these notes. Show all work. You can't just assume I know what your thinking is. You can't just say, oh, this thing, and then I did some stuff and now it looks like this thing. Well, you have to show me what that stuff is. You'll see what I mean in a minute. Do not invent new math. It's better to not arrive at the same answer than to make something up. And we always work vertically. We always work down the page. So here comes our first couple of identities here. Prove the following identity for all permissible values of the variable. So I'm going to make a little chart. Left-hand side and right-hand side. Well, this right-hand side is just 1. But the left-hand side is the sine of x times the secant of x times the cotangent of x. How do I prove that that's 1? Well, again, I'm not moving the 1 around. The 1 stays where it is, and I'm going to try to take the side that looks more complicated and see if I can prove that it equals the other side. So, what's the best thing? Okay, well, let's go back to my first hint. Oh, yeah. Why don't we just rewrite everything in terms of sine and cos? So let's go back and, whoa, come back here. Let's go back and do that. This one's already in sine. We'll leave it alone. But secant is 1 over cosine. And cotangent is cosine over sine. And I think you can see where this proof's going. Sine divided by sine is 1. Cosine divided by cosine is 1. 1 is equal to 1. And then you'd say, therefore, left-hand side is equal to right-hand side. All right, let's make a chart for this one. So let's see, what's my left-hand side and what's my right-hand side? So my right-hand side is the sine of alpha. The right-hand side is 1 plus the sine of alpha and 1 plus cosecant of alpha. All right, it is generally a good idea. They don't give us a whole lot of room here. I might have to end up moving the other side of this chart over, but okay. You're supposed to work down on these. Use as much paper as you like. All paper is made from criminal trees that deserve to die. Waste as much of it as you want. So let's see. 1 plus the sine of alpha. And the first thing they recommend is to change things to in terms of sine and cosine. There. Well, that doesn't look a whole lot better, does it? What if I make this a common denominator? Okay, so I'm going to just continue over here. I'm not going to, notice I'm not bothering to rewrite sine alpha on the right-hand side over and over again. I know I did it up there, I kind of rewrote the ones, but you know what, you don't need it. You know that this is your target. Your right-hand side has to eventually, your left-hand side has to eventually turn into sine of alpha. So how do I make that happen? I'm going to do a common denominator. This is 1 plus 1 over sine alpha, so I'm going to do my 1 trick. I'm going to times by sine alpha over sine alpha to this 1. So I'm timesing 1 by 1 if you really want to think about it that way, which doesn't change its oneness. But now the numerator is 1 plus the sine of alpha, and the denominator is sine of alpha plus 1 over sine of alpha. And, hey, is there any difference between 1 plus something and something plus 1? No, you can add things in any order you want. So I'm going to change this to 1 plus the sine of alpha times the reciprocal of this, which is the sine of alpha all over sine of alpha plus 1. And those two things cancel each other. And I have what's left over, sine of alpha, which equals the right-hand side. Done. Hopefully you're writing smaller than me. Okay, let's do the next one. I'll start my chart further to the left this time. Okay, so left-hand side and right-hand side. I don't need much room for the right-hand side because it's, again, just sine of x. I have to turn this thing into the sine of x. Okay, well, what am I going to do to it first? Again, helpful hint number one was, let's make everything sine and cosine. So let's do that. So secant is 1 over cosine. Tangent is sine over cosine. Cotangent is cosine over sine. I think I'm going to use my one trick all like doubled here. I am going to get a common denominator for this denominator here, which is going to be sine x times cos x. So I'm going to times this guy by sine x over sine x. And I'm going to times this by cos x over cosine of x. Again, that doesn't change what anything there is worth or equal to, because all I did was multiply by 1. Okay, continuing over here. So that's now 1 over the cosine of x. And what does this denominator look like now? Well, now it looks like sine squared x plus cos squared x. Did everybody get where I got those? From that makes that, and that makes that, right? And the denominator is sine x cos x. And like I told you, those equations that we looked at a couple pages ago are going to come in real important. What can you tell me about this line right here? What's sine squared x plus cos squared x? It's 1. So I can use an identity that I know is true and replace this line here with 1. So this is now 1 over the cosine of x. And this yellow part here is a 1. But again, if I'm dividing in fraction land, I'm going to multiply by the reciprocal. And 1 times the sine of x divided by 1 is just the sine of x, which is equal to the right-hand side. We're done. Proven. Okay, I think the next page they finally actually give me some charts to work with, and they've spread it out so that I don't try to cram 3 of them onto one page, so I kind of like this next page better. Okay. Now, anybody here good at chess? Anybody play some decent chess? Anybody who's played against anybody who's good at chess, or they're good at chess themselves, they know that what makes usually a player kind of superior to the player that they're playing against, I suppose experience is a big part of it, but also the good players are always thinking several moves in advance. And you know, that's actually not even just true of chess. That's true of, I'm a reasonably good pool player, but I missed some shots. But when I'm playing against guys who see the table better than I do, I can think of maybe my next couple of shots, and they've got the whole, they know the way their entire game's gonna, assuming they don't miss anything, the way it works out. I think it's even true of your more physical sports, right? The reason Wayne Gretzky was the greatest hockey player of all time was not because he was the biggest or the fastest or the strongest. None of those things. He was not the best skater. He was not the best stick handler, not the best shot. He just sort of saw the ice better than anybody. He had that creativity that he could think ahead of where you were thinking in a play. And I find identities are like that too. Now, I have to choose. Remember, we were told to only pick one side and work with it until it turns into the other side. You tend to pick the one that looks the more complicated. This side here isn't very complicated, and I'm already thinking ahead. I know what this equals. Need a refresher on what that equals? Go back to your identities page. One minus cos squared x is equal to sine squared x, because together they add up to 1. So I already know that when I'm looking at this identity that is now in front of me, that if I can turn this side, the right-hand side, into sine squared, I know that I've already figured out that it's going to work. So working backwards, I want this thing to become cosine. So let's now do the first hint that it told me. It told me to take the identity that you're given and convert things into sines and cosines. Tangent is sine over cos, so tan squared is sine squared over cos squared. The cos squareds cancel because they're dividing. And there you go. 3 steps and I got it. All right, let's try the next one. Let's see. Sine x cos x to me seems like the least complicated side. So I'll leave that one alone, and I'll see what I can do with the left-hand side. Okay, so I'm going to start by changing cotangent to sine over cos. Oh, sorry. How about cos over sine? That's better. Cotangent is cosine over sine, not sine over cos. Then I'm going to use the trick we've already seen a couple times today. Instead of dividing a fraction, I'm going to multiply by its reciprocal. And there we go. Does it matter what order you multiply two things in? Nope. There we have it. Okay, next one. What are we going to do with that? Well, the one on the left has powers of 4 in it. The right-hand side, it has a squared. I think I'm going to leave that side alone, and I'm going to work with this side. So the cosine to the power of 4 of theta minus the sine to the power of 4 of theta. What can you do with that? I'm going to work with the left-hand side, and here's what I'm thinking. I'm thinking, do I know something about x squared minus y squared? Yep. You should remember from grade 10 that when you factor a difference of squares, you get conjugate pairs. So if I had x to the power of 4 minus y to the power of 4, I'd get x squared plus y squared and x squared minus y squared. So that's what I'm going to do there. I'm going to change this to cosine squared theta plus sine squared theta and cos squared theta minus sine squared theta. There. Factored. Anybody hazard a guess as to what my next step is? I'll let you think about it while I print off attendance for this class here. Attendance, okay. Guys at home, I did your attendance. What do you notice? Well, I notice that this side doesn't have any cosines, right? So I have to make the cosines go away. Anything about this bracket that you notice? What's sine squared theta plus cos squared theta? It's 1. So I can replace this bracket with 1. And in this bracket, I don't want cos squared. What can I replace cos squared with again? Oh yeah, cos squared theta is 1 minus sine squared theta. So again, let me use my highlighter. I replaced this thing with 1, because my identity says I can. And I replaced this thing with 1 minus sine squared theta. And now it's just a matter of collecting like terms. Timesing 1 by anything doesn't change it, and that's negative of something minus another one is minus 2 of that something, which is the right-hand side. Math curriculum, I've been in this business a long time. I started teaching in 1994 in high school. I switched over to junior high. I was in a small high school in northern Manitoba for my first 5 years of my career. So I've seen the curriculum change a bunch of times. Not to mention it was totally different when I went to high school. But this has been a constant in grade 12 math. They did try. There was a movement to try to get rid of these things called trig identities. People looked at it and thought, well, this doesn't have a ton of applications in the real world unless you're doing some really high-level trigonometry type stuff. People, the course is called pre-calculus. I don't know that this does a whole lot of preparing people for calculus, but there were enough people to protect this. There was enough fans of trig identities, because what we like about it is that you can be not even all that great at algebra. You can be terrible with numbers. And as long as you have good logic and reasoning skills, this is excellent at kind of helping you work on your logic and reasoning skills. In fact, there was a time back before it was even called pre-calculus math, back in the old days. Some of your parents would have gone through Manitoba education when it was in grade 9 wasn't part of high school. High school started in grade 10. And we took in grade 10, you took math 100. In grade 11, you took math 200. And then in grade 12, you took math 300. This was in math 300. It's been part of grade 12 math for forever. And in those days, you were not even able to apply to the University of Manitoba without math 300, even if you wanted to do arts and stuff. So finally, when the curriculum changed and we split math 300 into kind of applied math and pre-calculus math, and different parts of the courses switched around, I remember that the pre-law guys still, even though all the arts guys were like, oh good, if you have applied math or even essential, in those days they called it consumer, even consumer math, you can get into the University of Manitoba and get into arts. But the law guys kind of stayed adamant that no, we want pre-law students to have pre-calculus math. It's like, but when you go to law school, you're not going to be doing any calculus. But they like this. They like proof trig identity problems to be something that students have done, because they like the logic of it, the reasoning of it. You have to build an argument, and that's something that appeals to lawyers, I guess. So, I don't know if you found that story all that interesting. I found it interesting. Anyway, now it's time for you to try some. So this page here, what page is it? It says exercise 15 because we stole it out of an old exercise book. It's page 10 in the booklet. This is part of your homework. I think actually maybe before you tackle this page, this is you should do second. The first thing you should do is the 6.1 page in the assignment book. Oh, you're going to need an assignment book. I gave you the notes, but you need the assignment book too. So here's the assignment book right here. And the 6.1 page, there it is. First of all, it asks you to do some non-permissible values, and then it asks you to do some simplifying. Then it asks you to prove that this is true using a number. Then, so this will be the first thing you do. So you do that first. And then jump to 6.3 and proving identities. So this will be the second assignment. And then that page 9 in the notes will be third. So there we go. So you have the rest of this class and all of tomorrow's class to work on from the assignment book, 6.1 and 6.3, and then from the notes package, what is it, page 9, no, it's page, I guess it's page 10, yeah, page 10. And so that's all due for Wednesday. So you have the rest of this class, and we'll give you a work period tomorrow. Now, under normal circumstances, I love the work period for trig identities because I usually get people to get up and work at the boards, and we can kind of look and see what each other's proofs look like. Of course, in COVID, we can't do that. But we will try our best to kind of share the way that we approach some of these, because some of these are quite tricky. Like look at, for example, look at 6C. What would you want to do with that? First of all, which side to you seems like the one you'd want to work on? I'm going to work on the left. I know cotangent could be turned into sine and cos, or cos over sine, but it's still definitely a simpler looking side than the left. These are so much fun. This is one of the most fun things I think we do in this course. All right, I guess I could stop my lesson now. I'm just rattling on at this point. Okay, so stop the recording. Oops, that's not what I wanted. No. Stop the recording.